So what we'll do today is discuss Bayesian networks, syntax and semantics, to set the grounds for the following discussions on applications. And as we kind of hinted at before, a Bayesian network has two components, a qualitative or a graphical component, as you see up there, which is this particular tag. And then there is another component, which is a numerical component that kind of quantifies the DAG structure. And together, they do specify a probabilistic state of belief, or what we have called a probability distribution. So what we'll do initially is first look at the qualitative component, which is the DAG structure you see up there, and see how we can interpret it as a set of conditional independent statements, as we hinted at before. That is, when you draw a graph like this, we will view this as a set of independence constraints. And those constraints do somewhat constrain the probability distribution that we're trying to specify, but they do not pin it down. And then we'll see when we add the numerical annotations, those numerical constraints together with the independence constraints will pin down one unique probability distribution. And you'll get to know how to do all of this today. But let's start with the reading of a DAG structure like this as a set of independence constraints. And here's an example. And the basic idea is that to see that if you do agree with the causal perceptions that are communicated by this DAG, then you tend to also agree with certain independent statements. So for example, in this particular case, if you see causality this way, and you do get a report that there was an earthquake, then that would likely change your belief on whether you're going to receive a call from your neighbor or not. The idea here is this report increases your belief in an earthquake. When your belief in an earthquake increases, that also increases the belief in the alarm triggering in your house. And then that actually leads you to believe that you may be getting a call from your neighbor. So these two guys are dependent in this particular case. Information about one of them influences your belief about the other. However, suppose that for some reason you know for sure that the alarm did not trigger. That's given information, right? You know the alarm didn't trigger. In that particular case, information about R will not change your belief about C. So basically, C is independent of R given that the alarm did not trigger. In fact, the reason why information about this changed your mind about that was because of this flow of information that way. So what happened here is, because of the way you understand the causality in the domain, you basically, that implies certain independence information. And this is just an example. What we're going to now see is that there's a whole set of independence constraints that can be read from a DAG, as we just did. So let's do that. Let's go ahead and show what is the general pattern here. All right. To be able to state the general set of independence assumptions that are implied by a DAG, we need just to make sure that we're clear on the following notation. The parents of a node are just the variables that are pointing to it in the DAG, right? So here's the parents of V. These are variables n with an edge from n to V, right? That's the classical definition of a parent. We also need the notion of a descendant. The descendant of a node V, if you look at the graph structure, basically there are all of the nodes that can be reached from V by following a directed path. Right? So these are variables n with a directed path from V to n. And the final thing we need is the notion of a non-descendant. And for that, we're going to take the non-descendant of V to be variables other than V itself, its parents, and the descendants. So we need these notions. And here's basically the set of independence assumptions that are encoded by a Bayesian network structure. Let's look at it for a second. And it is a template that applies to every node in the DAG. So here we're looking at a node V, and we're saying that given the parents of V, then V becomes independent of its non-descendants. And this applies for every node V in the DAG. All right? This is the set of independence assumptions. So if you have a DAG that has 5 nodes, then you have 5 of these statements. And this set of independent statements, we call them the Markovian assumptions of the DAG D. Right? So we're going to take a concrete example in just a little bit, but that's basically what's going on. And if the DAG has a causal interpretation, then you can think of the parents as the direct causes of V, and then the descendants as the effects of V. And in that case, this reads, given the direct causes of a variable, our beliefs in that variable become independent of its non-effects. Now, let me stress again, and we're going to get to this point later, Bayesian networks may or may not be causal, and this reading of independence still stands, and we'll have more to say about this later. But let's take a concrete example and make sure we're good with this. So here's the Bayesian network structure with 5 nodes, and what we're going to do is we're going to walk through these nodes one by one and see what this independence assumption say. And I want you to help me here with this. So we're starting with the variable C, and I'm going to contribute the variable. So each one of these independent statements have 3 components: the variable, the parents, the non-descendants. So I'll contribute the variable, you contribute the parents and the non-descendants. So in this particular case, what are the parents of C? It's just A. And what are the non-descendants? Right? So all of these guys are the non-descendants. Good. So here's what we have. So this DAG is saying that given A, C is independent of these 3 other variables. And here's the next guy. We're going to go to R. And in this case, also there is only one parent, which is E, right? And the non-descendants are also all of these 3, correct? So now this is what we have. That's another statement that's declared by this DAG. And now let's go to a variable A. So A is here. And in this case, the parents are so E and B. And what are the non-descendants? Only one guy, which is this, right? That's R. Excellent. And that's another independent statement. And now we're going to do B, right? So parents, nothing, empty set. Non-descendants, these 2 guys only. Very good. And finally, we have E, no parents as well. And there's only one non-descendant, which is B, and here we go. Right? So this is the set of what we call the Markovian assumptions of this particular DAG. Again, the interesting point is you draw this guy, which up until we started doing this looked a very innocent and just very intuitive thing. And we're taking it as these. That's quite a bit of information when you look at it as far as your own beliefs, right? I mean, look how much you've told us about your beliefs by drawing a graph like this. It's pretty interesting. You're going to see later also some of the implications of what's going on here. Let me mention one more thing, though, which is an implication. It's an observation here. If you look at a root node in a DAG, right? No parents, correct? So you're always going to have that node given nothing. And what are the non-descendants? The other roots are also non-descendants. So in fact, what you're going to find is in a Bayesian network, the roots are always independent from each other. All right? We'll talk more about this. So let's move on and look at another example from this. By the way, there is a number of probabilistic models out there that are not called Bayesian networks, but that have their own names. And some of you may have even studied these in other courses, but they are actually special cases of Bayesian networks. One example, how many of you have heard of Markov chains? Right. So those are special case of Bayesian networks. In fact, when you studied Markov chains, we're going to go over this in a little bit, you've studied the characteristic properties of these. That will fall out from the Markovian assumption, as you'll see. How many of you have heard of hidden Markov models? Okay, and these are also special type of Bayesian networks. In fact, what you're seeing up there is an example of a hidden Markov model in the notation of Bayesian networks. What we have here is a dynamic system that has a state, and the state, of course, changes over time. So you can think of the S variables here as the state of the system. So this is the state at time 1, state at time 2, and so on. In fact, this part here, ignore this guy. If you just look at this guy here, that is a Markov chain. And again, let's ignore the O's and just think about the guy up there. If you look at the Markovian assumption, what does it say? It says, for example, for state S3, it says, given S2, then the state at time 3 becomes independent of the state at time 1. In fact, more generally, if you pick a state at time t, it says, if you know the state at t minus 1, right, then my belief in the state at t becomes independent of all of the past. That's actually the Markovian assumption for Markov chains. Now, here we're doing the next step on Markov chains, what people call hidden Markov models. So the idea is, I do have these states, but I cannot observe them for the system. Instead, I have a sensor that actually tries to read that particular state. So these are the O's. And as you can see, the sensor reading is also time dependent. So O1 is the state of the sensor at time 1, and so on. And now we get this particular DAG, right? Now, if you look at how this is typically used, and we will do that later, you typically observe the state of these sensors, and then you say, given that these are my sensor readings, what is the probability that state 1 will be this or that? Or sometimes you find what is the most likely instantiation of these states. Again, interestingly enough, there is about, I think, 3 different algorithms that you can do the hidden Markov models, and they have their own names. When we study algorithms for Bayesian networks, they will all fall as special cases of what we will study later, including to some other things. But let's go back to what does the Markovian assumption says in this case. The Markovian assumption in this case basically says that once we know the state of the system at the previous time point at t1, so t minus 1, our belief in the present system state at t is no longer influenced by any other information about the past. If we look at it as an equation, or formally, here's how it looks. For state st, the parent is st minus 1, correct? And the non-descendants, in this case, look at S3, for example, right? Everything here is a descendant, right? And then these guys. So the non-descendants are basically, then you get this particular thing. So for ST, given ST minus 1, then it becomes independent of all of the previous states and all of the previous sensors. If you've studied hidden Markov models, you were actually given this equation as the characteristic property of hidden Markov models, but you can see now how it falls as a special case in this particular thing, right? Okay, folks, so let me here mention one more important thing, which we will get back to later when we discuss causality. So this is an important observation before we look at how we annotate these particular DAGs to get a fully fledged Bayesian network. The interpretation of DAGs in terms of conditional independence make no reference to causality. That is, when I show you a DAG and I say, here's the Markovian assumptions that correspond to it, right? We didn't talk about causality, right? We just said parents, descendants, non-descendants. Now, if you construct a DAG based on causal perceptions, you will tend to agree with those independence assumptions, as we kind of informally argued so far. But it's possible that you will have a DAG that does not match our causal perceptions, and still we would agree with the independence assumptions it's making. Now, that's hard to do in general manually, but let me just show you something. You can do it actually automatically. Look at this. On this side, we have the one that we've been looking at. This is the DAG that you would view as making sense from a causal point of view, right? And we looked at these, or some of these independence assumptions, and they made sense. correct? Now look at this guy here. This is a DAG over the same set of nodes, but you would not view this as causal, right? You've got alarm pointing to earthquake, causing earthquake, and causing, but that doesn't, right? Okay. Here's an interesting observation. If you use our Markovian assumption criteria and look at this DAG and write down the independent statements that it makes, you will agree with those. Assuming that you have already agreed with the independence assumptions that this guy made. Now, why am I making this claim? Because it happens that every independence statement made by this DAG is actually implied by those made by that. How did we make sure that that is the case? There is a construction process, a procedure that's in chapter 4. We will not cover it now, but we will probably do this when we do causality, that allow you to construct these guys in a systematic way so that you have this particular property. So if you agree with the guy on the left, you must agree with the guy on the right, even though it doesn't have a causal interpretation. That makes sense? And these also sometimes you can learn them, right? So you can sometimes learn a structure from data while only ensuring that the independent statements that it makes are okay, even though it actually may not be causal. And in a sense, if all what you want from the Bayesian network is the distribution, then you're okay. Once more, the causal one would be important because it carries more information than just the distribution that we're talking about today. If you want to do some other kind of queries that go beyond classical probabilistic queries, then you need the causal one. But again, this is something that we'll discuss at length later. Okay, folks. So now we get to the second component of a Bayesian network. So as I said, our main point here is to pin down a probability distribution over the variables. And there is an infinite number of distributions over these 5 variables, and the constraints, dependence constraints that are implied by this DAG kind of threw some of them away and kept some. So it narrowed down the set, but it did not pin it down. So now we're going to see what we need to do in order to pin down a unique distribution. And at an intuitive level, what you really would require now is to quantify the relationship between each node and its parents. That's what we're going to do. And for this, we need basically these probabilities. So if you look at a variable x, remember, big X is a variable, and its parents bold big U, then I need a probability of this form that tells me what is the probability of every state of the variable X given every state of its parents U, right? If you look at this particular DAG, it means we need the following. So for this variable C, I need probability of C given A. How many of these there are? Remember, C is one state. Small c is one state of the big C, and small a is one state of the big A. So these are variables are binary. So there are 4 numbers. This guy is a template for 4 numbers, right? Depending on what C and A is. Okay. And for R, this guy, I need this. And for A, I need this. How many of these? 8. And then for the root E, this guy, and for that. Okay. Now, the way we do this is by building tables that look like this. So for every variable, in this case, we're doing it for the variable C, and it has a parent A, we build a table that looks like this. This is A, the parent, and this is C, that's the variable, and these are all possible combinations, and this is the probability of C given A. All right? We call this a conditional probability table. And we can have one of these for every node in the DAG. Okay, stare at this table for a little bit. You're going to see these guys a lot later, especially when we do inference, for example. Inference algorithms will be operating on these guys. Now, the one observation to make is, if you really look carefully here at this table, or even though it looks flat, 4 rows, what it really represents is 2 distributions, right? When A is true, then that's one distribution over the variable C. And when A is false, that's another distribution. So it's actually two distributions over the variable C. One conditioned on A being true, and the other conditioned on the variable being false. Right? We're good so far? The other observation I want you to make is, even though this table has 4 numbers, some of them are redundant, meaning I can infer them from the others. Right? Because if I have a distribution over C, 2 values, true and false, if you give me one, I know the other. If the variable has 3 values, then I need just 2, and I can infer the third. So we would say in this case that not all of these 4 numbers or parameters are independent. We actually, only 2 of them are independent. The others can be inferred. And that's what this guy is saying. So if you look at this network, you will find that actually you can fully quantify it by using 10 independent probabilities to specify the CPTs. All right? You need only one number here. You only need one number there. That's 2. For this guy, you only need 2 numbers and 2 numbers here. And for this guy, you need only 4. So if you add up these, you're going to find that with 10 parameters, you can fully quantify this particular Bayesian networks. Okay. So a Bayesian network for a set of variables Z is a pair. G is the DAG, and theta is the set of parameters. G is a directed acyclic graph over the variables called the network structure, and theta, big theta, is a set of conditional probability tables, CPTs. We call these the network parameters or parameterization, and we're going to use this notation, especially will become very relevant when you do inference. We will use this to refer to the CPT for a variable X and its parents, right? X is a variable in the network, and bold big U here is the parents. X and its parents is called the network family. It's a term that we're going to use more later. And sometimes this probability is denoted by this. And we call this a network parameter. Right? So you're going to see this notation a lot, this guy here. Theta X given U. These are the numbers that appear in the CPTs. Okay, here's a fully fledged Bayesian network, both the DAG and the CPTs. So this network has 5 nodes, and therefore we have 5 CPTs, as discussed earlier. All right? Now, the question is, if I give you a network like this, and I tell you what is the distribution that is specified by this Bayesian network, because now we're making the claim that if you take the independence constraints of the DAG and these constraints, numerical constraint, there is one and only one distribution that satisfies these. We're making the claim now. I'll show you what this distribution is. Actually, it's very easy to construct that one. But then later we will prove why that is the case. Why do these constraints imply that guy? We need a little bit more material, so we'll do it later today. But let's first see what is that distribution. And here we just need one piece of notation. So a network instantiation is an instantiation of all network variables, right? So if the network is over bold big Z, then this small guy, that's one particular network instantiation. Just take all of the variables and fix the value of each. Now, here's an important notation that's used quite a bit in your book. This says the network parameter theta X given U is compatible with a particular network instantiation. And what does that mean? This is an instantiation of all variables, correct? This parameter mentions a subset of these variables, and it also fixes their values. I just want the values to be compatible, all right? Means that this instantiation and that are compatible. They agree on the values they assign to common variables. Let's take a concrete example. We have the variables A, B, C, D, E, and here's a particular network instantiation. So A is true, B is true, C is false, D is true, and E is false, right? That's one particular network instantiation. That would be this guy Z. These parameters are all compatible with this guy. For example, if you look at this guy, what does it say? E prime given C prime. Both E and C are primed in this case, correct? If this was E given C prime, that would not be compatible with this guy. Straightforward, right? but it's pretty important because it comes out a lot. Now that we have this, look at the following semantics for Bayesian networks. Which one? No, we're looking at the subscripts. So you're looking at this parameter. I don't care what its value is. I care what it refers to. This guy refers to the variable d being true, and the parents b and c being true and false. So this number, whatever it is, represents the probability of d being true given that b is true and c is false. Correct? Okay. This is a variable instantiation that also fixes the value of every variable. And what we're saying is wherever this guy is referencing is compatible with this instantiation. They assign the same. So variable d is true here, variable d is true here. Variable b is true here, variable b is true here. If the variable b here was false, that would not be compatible with this guy, right? Here's the distribution that's induced by a Bayesian network. Look how simple it is as an equation, and then we'll look at a concrete example now. Remember, the Bayesian network in this case is over the variable z. So this guy, small z bold, is one particular instantiation. If I show you how to compute the probability of this, we're done, right? You just use it for every possible instantiation. And what this guy is saying is pretty simple. If you give me a network instantiation, you fix the value of every variable, and you want to know what the probability of that is, collect all network parameters that are compatible with that instantiation and take their product. That's basically it, right? That's and this is, by the way, is known as the chain rule for Bayesian networks. Let's look at this example. Now, once more, if I give you now a full variable instantiation, here's an observation you have to really know. Remember, how many parameters for this guy? These are all binary. How many parameters here? Not the independent, all of them, 2. 1 for A being true, 1 for A being false, correct? How many parameters for this? 4, correct? For the different combinations of B and A, right? Here's a question I have to ask you first. You have to internalize this. If I fix the variable instantiation, for this guy, one of them will be compatible with that instantiation, precisely 1. What about this guy? Precisely 1 out of the 4, and so on. In fact, for any variable instantiation, there will be 1 from here, 1 from here, 1 from every CPT. Precisely 1. You take these and take their product, and here's the example. What is the probability of A being true, B true, C false, D true, and E? It's obvious. You just go to every guy. Let's say here, theta sub A. This guy, D given A. This guy, C prime given A. Right? And so on. Very easy. So now we're going to talk a little bit about the size of a Bayesian network, because that's a big deal. If you look at a particular CPT, this guy, for a variable x and its parents u, as you can imagine, the size of this is actually exponential in the number of parents, right? Because I have to look at every instantiation of the parents. If every variable has d values and at most k parents, the maximum number of parents is k in the Bayesian network, then this is the bound on the size of a CPT, right? And since I have n of these CPTs, the size of the total number of CPTs is this. So it's linear in the number of variables and exponential in the number of parents. If the number of parents is bounded, then this is pretty good, right? This is basically linear. Now, remember, a probability distribution over n variables is exponential in the number of variables. And now I'm specifying it compactly, right? In basically linear space, specifying an exponentially sized distribution. Now, of course, this is assuming that the number of parents is small enough. So what happens when the number of parents is large? So people have been studying ways to come up with more efficient representations for these CPTs that are not tabular and therefore not exponential. In chapter 5, we look at some of them. The ones that are more successful are specialized. They do not always apply. They apply in some situations. But you remember in our first lecture, the introduction, the very last lecture, we talked about the notion of structured Bayesian networks. And we talked about it in the context of doing maps and hierarchical maps. Okay. One of the main things about structured Bayesian networks is doing something about this problem, where it proposes a new representation of CPTs that would be can be efficient even if the number of parents is very large. It's not necessarily exponential. Now, we have two more topics to cover. They're both about the independence information that is encoded by a Bayesian network. And this story, as I said, has two parts. So the first part is this. If you look at the Markovian assumptions, you list them there, and you read them literally, there are things that follow from them because probability satisfy some properties. So there are properties of conditional independence that you can use to drive some of these implications algebraically. And the first part of the story, we're going to list them for you because they're pretty interesting. And some of them are surprising, right? We'll do those. But when you look at it and you say, wait a minute, so am I really going to be sitting and doing these things, manipulating equations to find implications? No. There comes the second part, which is the interesting one. There is a graphical test that I give you the DAG, and you do some graphical criteria on it, and you can infer these implications. You don't have to do any algebraic manipulations. We will show a test called deseparation that if you apply, you can find all implications of the Markovian assumptions. And that's going to be the ultimate reward here today. Here's the first property. It's called symmetry. And what basically this says, if X is independent of Y, in fact, I'm going to try to use more relevance today. If Y is irrelevant to X in the presence of Z, that once you know Z, Y becomes irrelevant to X, then the opposite is also true, right? Learning Y does not influence our belief in X if and only if learning X does not influence our belief in Y. So just to give you a quick example here, if you look at this DAG and you look at the Markovian, you find that this thing is there in the Markovian assumptions. Using symmetry, then we can also get this by just flipping the A and R. But that's not literally inside the Markovian assumptions. This is one example, right? Symmetry. And now we're going to do another property earlier. Here's how the axiom looks. It says this implies this and that. Now, what is it really saying? It's saying if these two sets of variables, y and w, are irrelevant to x, then each one of them alone is irrelevant. Another way of doing this, if learning this information does not influence our belief in x, then learning y alone or learning w alone will not influence our belief. Yet another way of stating this, if some information is irrelevant, then every part of it is irrelevant. And what this means is, look at it from the Markov assumption. If you look at this model here and you look at B, where is variable B? Here's variable B. Given S, it becomes independent of the non-descendants, these guys. What the decomposition allow you to do is basically to take any subset of these and you'll be okay. That's I think, the question you raised. So it's not just literally all of these the state of all of these variables, but the state of any subset of them. Okay, now we're ready actually. Now that we have, so what did we do? Symmetry and decomposition. Now we're actually ready to prove the semantics of Bayesian networks. Why is it that that distribution that I showed you works? Right? And here's how we're going to do it. Remember, you can specify the semantics of a Bayesian network by just telling me how to compute the probability of an instantiation. And For this Bayesian network, these are the 5 variables. Now, what is this? Remember the chain rule from last week? It says if you want to compute this, that's probability of R given everything that follows, and then probability of C given everything that follows, and so on. We're good so far? Okay, now, we will simplify some of these terms. This is not what I told you. This is not the way I explained to you how to get the property of a Bayesian network, in a Bayesian network, right? Okay, but look what we're going to do now. We're going to simplify these terms using the independence information in the DAG. Look at this guy. What does this say? Probability of R given what? Given everything else. What is that equal to? This is the parent, and these 3 are irrelevant given the parent. So then this guy simplifies to that. You see that? So if you look at this guy here, similarly you can simplify it to C given A, and so on. So if you do these simplifications, what do you get? You get this, which is what I told you. Effectively, you're going for every node and picking up the corresponding compatible parameter, and we just, starting from the chain rule of probability calculus and using the dependence assumptions of the Bayesian network, we proved the chain rule of Bayesian networks. Good? Okay. Now, if you go home and try to impress someone, say, let me show you how this works, and do this, you may not get what I just get. Okay, there's a trick in what I did here. I need you to be aware of before you fail to impress your friends. The reason why this worked is because when we did this trick, when we did this derivation, those variables were ordered in a particular way. If they're ordered not according to the way that I'm going to mention, this will not go through, right? You need basically those to be topologically sorted. And the idea is you need to order them so that when you do the chain rule for Bayesian networks, for probability calculus, every term that looks like this, the parents of X has to appear after the bar, right? So the instantiation of its parents is guaranteed to be in alpha, and the only other variables in alpha beyond the parents must be non-descendants. So to do that, you have to have basically a topological sort of the, and then this works. So but then it generalizes. Okay, and here's a couple of other examples using other orders. Right? Different than the one that I showed you, but basically consistent with the topology of the. Okay, so we're at our break time, and this is a good time to break. So here's what's left. We did symmetry and decomposition, and we utilized. We interrupted our discussion to utilize decomposition to prove the semantics of Bayesian network. When we come back, there's a few more properties about independence that again are intriguing in why they hold or not hold, as we will see. And then once we do that, we should be able to do that briefly, and then we will talk about that graphical test that allows us to not use these equations and just nicely and visually and graphically find all of the implications implied by them. So 10-minute break.